Okay, let's dive right in. You've handed us this stack of material, looks like lecture notes on matter and energy.
That's right.
And our mission today really is to unpack these notes. We want to get to the absolute core of what matter and energy actually are, how they behave, how they interact,
Mhm.
and why understanding this stuff is, well, it's like getting the blueprint for everything you see around you, isn't it?
It really is.
I mean, just look around you right now, the chair you're sitting on, the device you're listening with, even the air, it's all made of something.
Yep,
And this deep dive is all about digging into that something, using these notes as our guide.
exactly. And it's not just, academic theory stuck in a textbook. These concepts explain everyday things, why ice melts, how your phone battery works,
Or cooking dinner tonight.
right, why cooking changes food. So, yeah, the goal is to pull out the key ideas from this material, make them clear, and hopefully pretty interesting for you.
Okay, let's start unpacking. The material kicks off with the absolute basics. What is matter?
The foundation.
And the definition it gives is pretty straightforward. Anything that occupies space and has mass.
Seems simple enough.
Yeah, and it lists the usual suspects, steel, water, wood, plastic, stuff you can touch and see.
Tangible things, sure.
But then right away, the material makes a really important point, I think,
Which is,
that matter isn't always obvious. It can be invisible, like air.
right, air definitely occupies space, the room you're in.
Okay.
And it has mass, even if it doesn't feel heavy. Or think about microscopic dust, can't see it without help.
Uh-huh.
So this really hammers home that matter is literally everywhere, even when you can't perceive it directly.
Okay, so occupies space, has mass visible or not. Got it. But then the notes say, well, matter isn't just some smooth, continuous goo.
No, definitely not. It's made of tiny, discrete particles. That's a huge concept.
And ultimate building blocks,
Atoms. It all comes down to atoms. Everything physical is composed of atoms.
which then connect together, right?
Exactly. Atoms bond in specific ways to form molecules. The notes use water, H2O. It's a classic example.
2 hydrogens, 1 oxygen stuck together chemically.
And that's totally different from, say, the carbon atoms in graphite, which are just carbon atoms but arranged in layers. The way they bond and arrange makes all the difference.
It's like Legos, sort of. Same bricks, different structures.
That's a good analogy, yeah. And what's really cool, highlighted in these notes, is how we can see this now.
See atoms. Really?
Well, yeah, with things like the scanning tunneling microscope, the STM. The material mentions seeing images of individual nickel atoms,
wow.
looking like tiny spheres, and even imaging DNA molecules, where you can actually make out the double helix structure.
That's incredible. It makes it so much more real than just, abstract diagrams.
It really does. Brings the submicroscopic world into view.
Okay, so matter is made of atoms and molecules. Check. How does this stuff actually, appear in the world? The notes move on to the states of matter.
Right. The common states. Solid, liquid, and gas. And the state depends entirely on how those particles, atoms, or molecules are behaving, their motion, how close they are.
So solids first.
In a solid, the particles are packed really tightly together. They're basically in fixed positions. They vibrate a bit, but they can't really move past each other.
Okay.
And that fixed arrangement is what gives solids their definite shape and volume. Think ice, or a diamond, or piece of iron, rigid.
Makes sense. Then liquids.
In liquids, the particles are still quite close, but they have enough energy to slide past one another. They're not locked in place.
So they can flow.
Exactly. That's why the liquids have a fixed volume. The particles are still close, but they take the shape of whatever container you put them in.
Yeah.
Water, gasoline, mercury.
Gotcha. And gases.
Gases are a whole different ballgame. The particles are really far apart, zipping around randomly at high speeds.
Mostly empty space between them.
A lot of empty space, yeah. They barely interact most of the time. So gases have no fixed shape or volume. They just expand to fill whatever container they're in.
And that explains why you can compress them easily, like air in a bike pump.
Precisely. Because you're just squeezing out that empty space between the particles.
And the notes use water as the perfect example for all three, right? Ice, liquid water, steam.
Same H2O molecule, just behaving very differently based on energy, which usually means temperature.
Simple but effective.
And the material adds another layer for solids, which is interesting. It distinguishes between crystalline and amorphous.
Okay.
Crystalline solids have that super orderly repeating pattern of atoms or molecules, like a long-range order. Salt crystals being cubic, or the structure of diamond. Very geometric.
Like soldiers lined up perfectly.
Kind of, yeah. Whereas amorphous solids, they don't have that long-range order. The particles are sort of jumbled together more randomly. Glass is a classic example. Rubber, plastics too.
So more like a crowd than neat rows.
That's a good way to put it. Ordered versus disordered structure.
Okay, so we've got states of matter based on particle behavior. What about classifying matter based on what it's actually made of, its composition?
Yeah, the notes lay out a classification scheme for that too. The big first split is pure substance versus mixture.
Pure substance sounds pure.
It is. It means it's made of only one type of atom or only one type molecule, consistent throughout.
And a mixture.
That's when you have two or more different substances, different atoms or molecules just physically combined. And crucially, the proportions can vary. You can have a little salt in water or a lot.
Right. Okay, so drilling down into pure substances.
Two types there. Elements are the simplest form. They cannot be broken down into anything simpler by chemical means. They're the fundamental ingredients on the periodic table. Helium gas, for instance, is just helium atoms. Pure element.
Can't get simpler than that.
Nope.
Yep.
But if you take two or more different elements and chemically bond them together in a fixed definite ratio.
Then you get a compound, like water, always 2H for every O.
Exactly. Or table salt, NaCl, always one sodium for one chlorine. Sugar is another compound. And unlike elements, compounds can be broken down into their elements, but you need a chemical reaction to do it.
So the key difference between a compound and a mixture seems to be that chemical bond, that fixed ratio.
Precisely. In a compound, the atoms are chemically united. In a mixture, they're just, well, mixed together. Physically present, but not chemically linked in that specific way.
Okay, examples of mixtures. The notes mention air.
Yep, air is mostly nitrogen gas and oxygen gas mixed together. Seawater is a mixture of water and various salts, plus other things.
And the saltiness can vary, proving the variable proportion point.
Exactly. But then mixtures themselves can be subdivided.
Oh, yeah.
Based on uniformity. You have homogeneous mixtures where the composition is the same throughout. Like if you dissolve sugar completely in tea, every sip tastes the same. Uniform.
Smooth.
And then heterogeneous mixtures where the composition is not uniform. You can see different parts or it varies from place to place. The classic is oil and water. They don't mix uniformly, they separate into layers.
Like chunky soup versus broth.
Yeah, kind of like that. So the overall picture of the classification tree from the notes is matter splits into pure substances or mixtures.
Right.
Pure substances are either elements or compounds.
Got it.
And mixtures are either homogeneous or heterogeneous.
That's actually a really useful framework for thinking about, well, anything you encounter.
It gives you a mental filing system for the stuff the world is made of.
Okay, so we know what matter is, what it's made of, it states how to classify it. How do we actually describe it? The notes bring in properties.
Yes. And again, a critical distinction is made between two types. Physical properties first.
Okay.
These are characteristics you can observe or measure without changing the substance's fundamental chemical identity. Its composition stays the same.
Examples.
Like the smell of gasoline, you smell it, it's still gasoline. Water boiling at 100 degrees Celsius, you measure the boiling point, it's still water. Just changing state, density, color, hardness, all physical properties.
So you're just observing what it is.
Pretty much. Now, chemical properties. These are different. You can only observe a chemical property when the substance undergoes a chemical change, meaning its composition does change.
Ah, okay. So like
Flammability. Gasoline's ability to burn is a chemical property. To see it, the gasoline has to react with oxygen and become different stuff, carbon dioxide and water.
it changes identity.
Exactly. Or iron rusting. That tendency to rust is a chemical property. The iron reacts with oxygen and water to become iron oxide rust, a new substance. You only see the property during the transformation.
That makes sense. It's about its potential to become something else chemically.
Well put. And that leads right into the next topic, changes in matter.
Right, because matter doesn't just sit there with properties, it changes. And the notes give us two main types of change, too, mirroring the properties.
Yep, physical changes and chemical changes. And the core difference, again, is all about whether the chemical composition, the identity of the substance, is altered.
So a physical change.
Alters the appearance, maybe the state, but not the chemical makeup. The atoms or molecules are still the same, just maybe arranged differently or moving differently.
Like melting ice. It looks different liquid instead of solid, but it's still HO.
Perfect example. Or boiling water, crushing a rock, dissolving sugar in water, though that one can be debated a bit. The notes say it results in a different form of the same substance.
Okay. And things like filtering or distillation used to separate mixtures.
Those are physical changes too, because you're separating components based on physical properties, but the components themselves don't change chemically, You get salt back from salt water. By evaporating the water, both salt and water remain salt and water.
Right, so chemical change must be.
That's where the composition does change. Atoms rearrange, old bonds break, new bonds form. You end up with completely new substances with different properties. It happens via a chemical reaction.
Like the rusting iron example again.
Exactly. Iron plus oxygen yields iron oxide, new substance.
Okay.
Or burning wood plus oxygen yields ash, carbon dioxide, water vapor, all new stuff. The notes are clear. It results in a completely new substance.
Okay, physical change, same stuff, different look. Chemical change, new stuff entirely.
That's the essence of it.
Got it. Now, when these changes happen, physical or chemical, the material highlights a really fundamental rule, something that always holds true.
Oh, yes. You mean the law of conservation of mass.
That's the one. Matter isn't just created or destroyed out of thin air during these changes.
Absolutely not. In any chemical reaction or even a physical change, the total mass of all the substances you start with
The reactants.
must equal the total mass of all the substances you end up with.
The products.
Right. Mass is conserved. The notes do mention that nuclear reactions are a bit different. There's mass-energy conversion. But for typical chemistry, mass conservation is key.
And the notes give that butane burning example, which makes it really clear.
Yeah, the numbers.
You start with 58 grams of butane and 208 grams of oxygen. That's your input.
Total of 266 grams.
And you end up with 176 grams of carbon dioxide and 90 grams of water. Add those up.
176 plus 90. Also 266 grams.
Exactly. The atoms just rearrange themselves from butane and oxygen molecules into CO2 and water molecules, but all the mass is still accounted for. Nothing lost, nothing gained.
It's a fundamental accounting principle of the universe, really.
And that idea of conservation, it doesn't just apply to matter, does it? The notes bring in the other big player.
Energy. You can't talk about why matter does what it does without talking about energy.
So what's the definition of energy here? The notes say it's the capacity to do work.
Yeah, work in the physics sense, applying a force over a distance. But more broadly, energy is what drives change. It makes things happen. The behavior of matter is totally driven by energy.
And just like mass.
Energy is conserved, too. The law of conservation of energy. It's another bedrock principle. Energy can't be created or destroyed.
It just changes form.
Exactly. It can be converted from one form to another, like chemical energy, to heat energy when you burn something, or transferred from one place to another. But the total amount of energy in an isolated system always stays constant. It doesn't just vanish or pop into existence.
Okay. And the notes mention different forms. Kinetic and potential.
Right. The total energy is often thought of as the sum of kinetic energy, which is the energy of motion.
Particles moving faster means more kinetic energy.
And potential energy, which is stored energy. It can be due to position, like a ball held up high, or due to composition, the way atoms are arranged in molecules.
And the specific types listed were electrical, thermal, and chemical energy.
Yeah, those are common forms. Thermal energy is related to the random kinetic energy of particles. Chemical energy is a type of potential energy.
Stored in the bonds.
Stored in the chemical bonds in the arrangement of atoms, exactly. The notes explain that systems, like molecules, tend to move towards lower potential energy states because that's more stable.
Like the TNT example.
Right. TNT molecules have a huge amount of chemical potential energy packed into them. They're relatively unstable. That's why they tend to undergo a rapid chemical change and explosion, releasing that energy as they transform into simpler, much more stable, lower energy molecules like CO2 and nitrogen gas.
And that release of energy, that's exothermic.
Yes, exothermic reactions release energy, usually as heat, into the surroundings. Burning is exothermic.
And the opposite.
Endothermic reactions absorb energy from the surroundings. They feel cold, often, like some instant cold packs or photosynthesis plants use energy from sunlight to build complex sugar molecules.
Okay, energy drives change, and it's conserved. How do we measure it and measure its effects, like temperature?
Good questions. The notes cover units of energy first. The standard scientific unit, the SI unit, is the joule, symbolized J, named after James Joule, who did key work showing energy conservation during conversions.
Joule. Got it. What else? There's
the calorie, little c. That's the energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. A calorie is bigger than a joule, about 4.184 joules.
Okay. And then there's the one on food labels.
The nutritional calorie with a capital C. That's actually a kilocalorie at 1,000 of the little c calories.
Right. So that candy bar example in the notes, 225 calories.
If you convert that, following the steps cal to cal, then cal to joules, you end up with a huge number of joules, like over 940,000 joules. Shows how much energy is stored chemically in food.
Wow. And the last unit mentioned was the kilowatt hour.
Kilowatt, yeah, right. That's what you usually see on your electricity bill. It's a unit of energy, not power, even though it has watt in it. The notes even give an average cost, like 12 cents per kilowatt in the U.S., to make it relatable.
Okay, so joules, calories, kilowatt hours, ways to quantify energy. Now, about temperature.
Yeah.
The notes make a really important distinction here.
Yes. Temperature versus heat. People mix these up all the time.
So break it down for us based on the notes.
Okay, thermal energy is basically the total random kinetic energy of all the atoms and molecules in a substance, just their constant jiggling and moving around.
Right.
Temperature is a measure of the average kinetic energy of those particles. If the particles are moving faster, on average, the temperature is higher. It tells you how hot or cold something is, fundamentally related to that particle motion.
Okay, temperature is the average energy measure. What's heat then?
Heat is the transfer or flow of thermal energy. And this transfer only happens when there's a temperature difference between two things. Energy naturally flows from the hotter object to the colder object.
Like heat flowing from your warm hand to a cold ice cube.
Exactly. Heat is energy in transit. It has units of energy like joules or calories. So temperature is a property, a state. Heat is a process and energy transfer.
That's a super helpful clarification. Okay, measuring temperature, the scales. Fahrenheit, Celsius, Kelvin.
Right. Fahrenheit gauge F is common in the U.S. Water freezes at 32 degrees F, boils at 212 degrees Fahrenheit, room temp around 72 degrees Fahrenheit. The notes mention it was based on things like saltwater freezing and body temperature historically.
Then Celsius, degrees, used pretty much everywhere else and in science. Much simpler with water.
Yeah, 0 degrees C for freezing, 100 degrees C for boiling, room temp around 22 degrees C. Nice round numbers based on water.
And Kelvin, the science one.
Kelvin is the SI unit, an absolute temperature scale. 0 Kelvin, 0 K, is absolute zero, the theoretical point where all molecular motion basically stops. It's about negative 273.15 degrees C.
So no negative temperatures on the Kelvin scale.
Correct. Water freezes at about 273 K and boils at 373 K. Room temp is around 295 K. It's directly related to particle energy, which is why it's so useful in science.
And the size of the degrees.
A Celsius degree and a Kelvin degree are the exact same size interval. Changing by 1 degree C is the same temperature change as changing by 1 K. A Fahrenheit degree is smaller, only 59ths the size of a Celsius or Kelvin degree.
Which is why the conversion formulas aren't just simple addition or subtraction.
Exactly. You have to account for the different scale sizes and the different 0 points.
Okay, scales covered. Now, connecting energy transfer, heat, to temperature change, the notes introduce heat capacity.
Specifically, specific heat capacity, often just called specific heat.
What's that?
It's the amount of energy heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius, or 1 Kelvin, since the degree size is the same.
So it's specific to the substance.
Yes, very specific. The units are usually joules per gram per degree Celsius, JG degrees. And the notes point out something really interesting in the table provided. Water has a really high specific heat capacity compared to most other things.
Meaning,
it takes a lot more energy to heat up 1 gram of water by 1 degree than it takes to heat up, say, 1 gram of iron or sand by the same amount. Water absorbs and releases heat slowly.
Which explains why coastal areas have milder temperatures than inland deserts. The ocean acts like a giant heat buffer.
Precisely. It absorbs huge amounts of heat in summer without getting drastically hot, and releases it slowly in winter, preventing extreme cold. It's a direct consequence of water's high specific heat.
Cool connection. And the gallium example, the metal that melts in your hand.
Yeah, the notes use it to show a calculation. Gallium melts just above room temperature, around 29.9 degrees C. They calculate the heat needed to just warm up a small piece, like 2.5 grams, from room temp, say 25 degrees C, to its melting point.
Using its specific heat.
Right. You multiply the mass, 2.5 G, by the specific heat of gallium, which is 0.372 JG degrees C, according to the notes, and by the temperature change, 29.9 degrees C, 25.0 degrees equals 4.9 degrees C.
And that comes out to?
Comes out to about 4.5 joules, which is, a pretty small amount of energy. That's just to reach the melting temperature. Actually, melting it requires significantly more energy, called the heat of fusion, which your hand readily supplies. It's a neat little demo of these principles.
Wow. Okay. We have definitely covered a lot of ground from these lecture notes. It feels like we've built a whole picture.
We really have.
Started with just defining matter, anything with mass and volume, then realized it's made of tiny atoms and molecules.
Explore the states solid, liquid, gas, based on how those particles move and stick together.
Classified matter by what is made of pure elements or compounds versus mixtures, both uniform and non-uniform.
Homogeneous and heterogeneous. Then we looked at how to describe matter using its properties physical versus chemical.
And how matter changes physically altering form or chemically becoming something new, all while conserving mass.
Can't forget the conservation law.
Yeah.
And then we brought in energy, the driver of all this change, defined it, saw it's also conserved.
Looked at kinetic and potential energy, especially chemical potential energy stored in bonds.
Distinguished temperature, the measure of average particle energy. For meat, the transfer of that energy.
Yeah.
Covered the scales, specific heat. Yeah, quite a journey.
Hopefully, for you listening, this deep dive into the material has maybe connected some dots, given you a clearer picture of this fundamental stuff that makes up everything.
It really is the foundation. And maybe a final thought to leave you with, drawing from all this.
Go for it.
If everything around us, a grain of salt, a tree, a computer, even a living organism like you, is ultimately just atoms and molecules, arranged in different states, interacting according to these physical and chemical properties, driven by energy that's constantly being transferred and transformed but never lost. What does that really imply? How does understanding these fundamental rules about matter and energy change how you view the complexity and the maybe underlying simplicity of the world? Something to ponder, perhaps.